So that's everything that I need to cover for the moment about experimental data science. So let's take a moment just to start considering the differences between data science projects and software-led projects. The critical ones are these, and I'm going to take them all individually and then talk about them a little bit. When we talk about model training, and this is a term we'll hear very regularly when we are talking both about experimental data science and about established data science. It's just that with established data science, the model training has already taken place by the time you receive the model. With experimental data science, it's actual piece of work that needs to be done. Broadly speaking, the way it works is this. You get a bunch of data, and you tag that data to describe what it is. In this case, it's cat data, and I'm saying all of these pictures represent cats. You then feed that into the machine learning model, and it starts to learn what a cat is. And eventually you'll come to a point where it says, this is a cat. You put in a picture of a cat, it says, this is a cat. Brilliant. Well, of course it would. You told it was a cat, you tagged it with cat. So to validate it, what you do is you take a variety of images that have not been tagged as cat and are questions, and you feed those into the data science model, and it should be able to, if it's working and performing to a high enough level of accuracy, say, this is a cat. Bear in mind that for a human, recognizing a cat is very easy, but a cat might be sat up, it might be lying down, it might have its tail up, it might have its tail down, it might have its legs tucked in, it might have its ears back, facing forward, facing back. So all of these actually make the recognition of cat very difficult for a machine learning system, although very easy for a human. So training the data, training the system to recognize all those different permutations of cat is what model training is all about, so that it is able to recognize cat from any angle, standing, sitting, lying, etc. Next, we have model accuracy. We've talked about it a little bit up until now in the course of the presentation, but let's get into a little bit more depth. There are three parts to model accuracy. Model accuracy measures how performant a model is. That is, how well it is performing the task that is being asked of it. And this is often measured using a mathematical formula called R squared. There are lots of other ways of measuring it, but this is one of the most common. And this takes account, or this model takes account of how far the model is deviating from what is correct. And it takes account of both right and wrong, but also true negatives, true positives, and false positives and false negatives. As a result, it's way more complex than I need to get into in this conversation. But the point is, there is a mathematical way that data scientists are aware of to measure the accuracy of their model. Next, we have minimum accuracy, and this defines the minimum performance level that business is prepared to accept. And the target accuracy and minimum accuracy may be one and the same thing, but it's worth having the conversation to ask, what is the lowest level? How do we know when we are doing good enough? You still may want to go further, but how do we know we're doing good enough? And the business can then choose to invest more in getting better up to their target accuracy, but what is the minimum level they are prepared to accept? Obviously, this implies that target accuracy is the ideal level of performance the model needs to hit. These all need to be considered, and they all need to be considered and agreed at the outset. Having this conversation 3/4 of the way through the project is way too late, and it's way too late for this reason. Accuracy relates to value and cost. That is, the more accurate a model is, the more valuable it is. However, chasing a target accuracy will lead to a longer duration and a greater cost, because if your accuracy is, I don't know, 60% and your target is 80%, you need to invest more money to increase that level of accuracy. However, chasing a target accuracy can also lead to rabbit hole mentality, and it can lead to us spending more money to build up that level of accuracy and spend more money, and that spend may not necessarily be the best use of that accuracy. To avoid that, what we need to understand is the value of percentage increase in accuracy. That is, how much do we need to pay per iteration, per sprint, to improve the accuracy, and how much accuracy are we likely to get by that investment? If we use that typical example of a facial recognition system, we may want an accuracy of 70%, but find that we're delivering at 60%. And if we were only improving by 0.2% per iteration, we're going to need an awful lot of iterations in order to get up to that 70%. That may actually represent a poor investment of the budget, and it may be decided that 60% actually is good enough. Let's move on. However, if we're talking about an industrial plant where 0.2% improvement equates to $2 million of accrued value, suddenly it might actually be worth investing that same amount of money into another iteration to get that extra 0.2%, 0.4%, 0.6% improvement. And the point is that targeted minimum accuracy can be used to have a conversation about when to continue and when to stop improving on a model. And by having these conversations, having this data available, it means we're able to have those conversations in a less emotional way. We're not reliant on a data scientist and saying, hey, can you get it a bit better next sprint? Yeah, I can. How much better do you think you can get? Oh, I don't really know. By having these conversations, having these targets, having this data, we can actually make that conversation much more objective and much more informed, and then make the relevant decision about whether we continue making improvements or whether we stop there and move on to another part of the project. I did say that we would come back to model drift and detecting drift. And to start with, I'm actually going to read out these definitions. These are the official definitions, and I can't sum them up better than this. What is model drift? Model drift, also known as model decay, refers to the degradation of a model's predictive power due to changes in the environment, and thus the relationships between the variables. That is, when you get a model into a live situation, it will, over time, degrade and get worse at making predictions. If it is going to do that, we need to have a system in place whereby we can detect that drift. Drift involves statistical change in the data. The best approach to detect them is by monitoring its statistical properties of the model's predictions and their correlation with other factors. That is, we need to have some sort of statistic in place that is able to detect our drift. We talked about that a few moments ago. It's R squared. It is whatever method, whatever number you are using to detect or to track the accuracy. So detecting drift is very much a question of saying, well, how far are we away from that target accuracy? If our target accuracy was 70%, we went live with 70%, and 6 months later, we're now only achieving 60%. Well, we've detected the drift has happened, we now need to do something about it. And that do something about it is retraining the model. This is very, very common in data science systems. You have a model, you train it, you put it live, and periodically you retrain it on live data to ensure you achieve high levels of accuracy.